Assalamu alaikum. Okay, I think we should make a start for the second session, inshallah. For those who don't know me, my name is Abdeljalil Sultani. Well, I'm a member of the Nasr.org group and an editor in Inspire magazine. And in this afternoon, we're going to have two sessions. Well, it's actually one session with two presentations. The first in the field of computer science and engineering. And the second will be on medicine, pharmacy, and veterinary sciences. The first talk we're going to have is going to be presented by Dr. Abdeljalil Bennecer, PhD in optical communications from Cambridge University, and he's now a lecturer in Northampton University. And the talk will be titled "Reliability of Manual Ultrasonic Non-Destructive Testing." Okay.
I'd like to share some thoughts about my research topic. So it's not a research presentation. It's rather research thoughts that I would like to share about my related to my research. So Algeria infrastructure landscape is rapidly changing. We know that new motorways have been built, tall buildings are erected, and also old and new oil and gas pipelines need maintenance. For this reason, I suppose these structures require testing to test their fitness for service. So my topic will be about this a very well-established technique. It's called manual ultrasonic non-destructive testing, and its reliability. So we're all familiar with pyramids in Egypt, or the Great Wall of China, or even the Tower of Pisa, which is leaning but never falling. These structures transcend time, but we may be forgiven to think that they could last forever. Unfortunately, structures age over time, experience fatigue to become totally obsolete, like the picture on the top left, where you can see the motorway almost becoming unusable. The bottom right picture shows a decommissioned military aircraft at the end of its service. So there is also another mechanism. Cracks can also initiate in different structures due to loading, environment factors, or otherwise. The cracks grow and propagate, and they pose a substantial risk of failure. Without proper checks, catastrophic failures can occur, which may lead to tragic loss of life, interruption of service, long legal investigations, as well as heavy expenses. Some of you may remember the train accident which took place in Hatfield in Hertfordshire in 2000 here in the UK. The investigation, a later investigation, revealed that a rail had fragmented as train passed. So, for this reason, NDT, or non-destructive testing, is needed, is to ensure the integrity of the structures. So by using sophisticated equipment and a mixture of simple and complicated techniques, it is possible to ascertain the existence of flaws in components. What we need, for example, is the accuracy. That's what we need. And as just as to give you an appreciation, every year hundreds of repairs are carried out in different locations after visual inspections in London Underground tunnels. So this is something that's taken place every time. But the face of NDT is changing. At the moment, less NDT is used during manufacture. It's used for non-invasive inspection, but only during service. If you look at the demand, they now look for risk-based inspection or fitness for service, so they don't really they don't stop at NDT, they want to see whether it's fit for service. And also, there is an new methods are always introduced. For example, long-range ultrasonic techniques, time of travel, and diffraction techniques. And for those who work in the NDT, they find that those equipment become even more complex than they are, particularly in ultrasonics. And the population of NDT operators are also aging, so they are not new, fresh blood coming in. So using computers may be very challenging for them. And also the stringent training and qualification for NDT personnel. I'm going to talk about this in detail a little bit later. So the stress is that all these greater demands due to complexity, new techniques, computerized equipment, requires more training for NDT personnel without greater rewards. And that's perhaps the crux of the matter. And maybe as a result, very few people training for careers or taking a career path as an NDT operator. So we have a shortage of skilled NDT personnel. Now, looking at some of the methods, I think you've got one presentation. Anyway, so looking at the basic methods, there are about 5. In fact, now they become 7. The BINDT, the British Institute of Non-Destructive Testing, had added 2 more. Those are the most established techniques, from penetrant to magnetic. Both of those 2, but magnetic particle, are visual inspection, so they use the human eye. For the ultrasonic, an eddy current and radiography are the other 3. By far, if we talk about volumetric inspection, ultrasonic technique provides a high flow sensitivity. So by far, this is the most used technique. Just to give you a flavor, although I know this is non-technical talk, but I'd like to give you an explanation how it works. You've got an ultrasonic probe, as you can see. A pulse is fired from the probe, is reflected off the back wall, and then is received again by the probe. What you see on the screen are 2 pulses, the initial pulse and the back wall echo. Now, if there is a crack, the crack constitutes a discontinuity in the material. So it acts as a reflector. If there is a pulse, it reflects off that crack, and you get a peak between the 2 peaks. And that suggests that there is a discontinuity in the material. So basically, this is how it works. By knowing the speed of sound in the material, which we most of the time we know, and measuring the pulse round-trip time, we can calculate the distance. So there are many variations of this technique. This is known as a pulse echo, and there is also up to something that the most advanced is known as a phased array. Nevertheless, conventional manual ultrasonic still dominates. It's simple, cost-effective, and quick to deploy. Okay. I've been told that I've got only 3 minutes left, so I'm going to try and follow this very quickly. So this shows the path of an NDT operator. Perhaps the message to take away is how complex it is. For the aerospace industry, it takes about 3 years. It's almost like an undergraduate degree just to be an NDT operator. Not only that, look at the number of exams, what they need to do, the theory, the practice. They have to do a number of test cases before they can qualify. So those methods are limited, though. They can only provide whether they pass or fail. They don't tell them about the process. Also, they don't tell them whether they can sustain a good performance or even improve a poor one. Because at the end, what they look for is just they have found the flaws or not. So it's almost like a binary pass or fail. And also, if we look at the samples used, it's very expensive to cut out, to manufacture. Some of them, after say a structure has been decommissioned, they take samples. If we take a sample from an aircraft, a wing, that can be very large. That poses storage problems, for example. If it's from a power plant, sometimes they use radiography. and that means that it is hazardous, so that there could be some radioactive elements. This is to give you a flavor how laborious the NDT, the work of an NDT operator is. They have to take some, not only training in NDT, but sometimes they have to do even some tests in terms of their ability to be at a very high heights. MUT, despite its simplicity, it's suboptimal. A number of programs, those are trial studies that have taken place. The largest one is known as PISC in 1974. It finished in 2001. It's a worldwide trial study. Without exception, all of those have shown that MUT is suboptimal. In fact, the latest PANI shows that around 50%. There is a probability of 50% that an operator finds a flaw. Maury has compiled about 59 human factors that contribute to the reliability or probably unreliability of MUT, 12 of which are key and are listed here. So what is the answer? The automation? But there is no machine as dexterous as a human hand. And also, it doesn't get into very small places, intricate. The other problem is that sometimes it's only 1 meter. Deploying a robot is not very cost effective. So this is an approach that I coordinated when I was project coordinator of a European project. So we took a different approach. Instead of looking at the causes, the root causes, we looked at the symptoms, and that proved to be beneficial. Another work that we have done is the acoustic coupling, and we managed to get a 70% prediction accuracy, and we've also developed a virtual training environment. But I'd like also to give you a vision towards the future. So how can we make our structures last longer, be more reliable and cost-effective, making sensors integral part of the structure? This is sort of the vision. So we're moving more towards from unscheduled and scheduled maintenance to predictive. And this is a nice analogy. And I thank you for listening. Any questions?
Well, composites are being used more and more this day, particularly in the aerospace industry. I mean, you referred to the qualification of non-destructive testing engineers taking almost 3 years. How reliable is the technology in composite materials when you said that the technology itself actually depends on the speed of standing the material? And we know that composites are more often than not a composition of other.
There is no standard yet.
There isn't.
There isn't one. It's still underway. As you know, it's very complex. Different people have come up with different ideas. Ultrasonic seems to be the way to go, but it is very attenuative in composite materials. There is some work on eddy current, but in my view, it's very, very limited. What is proving quite beneficial nowadays is acoustic emission. Surprisingly, it used to be a method that is disliked by the NDT community. But in terms of composites, if they want to look at sort of weak points, that seemed to show some promise. But up to now, there is no standard yet.
I have a question. Next question. Yeah. No, actually, I had a question for maybe those of us looking for a job. What would you say is the reason for the lack of the new generation NDT operation? If there is, I mean, obviously if there's such a demand for it, why aren't there people? And if you guarantee the job after your 3-year course, why wouldn't you do it?
Not only you're guaranteed, even during your training, you're recruited, so you're paid. So not only that. The problem is that they work in very harsh environments. I mean, it's very risky. In most cases, they have to put up with a very low reward, particularly in terms of their salary. They get sort of bonuses because they travel all over the world. Obviously, they go to different places, but sometimes they are sent to Alaska, sometimes to Siberia, sometimes to the Middle East in scorching heat. So that's something that puts them off most of the time.
One more, sorry. You mentioned those Alaska, I'm saying, incorporating the sensors within the structure itself. Are there any real examples in today's world that use that kind of technology?
Oh yes, I mean, structural health monitoring, this is when you implement sensors. I mean, it's been in the realm of laboratories for over a decade now. It's never, but it remained confined in those spaces. The problem is that what you need to know about the NDT community is very, very conservative. If they want to make a change, it takes a long time, and you have to prove it. After all, they're concerned about the safety, so they can't compromise. And it happens to most of those fields where safety is a paramount feature. But mainly because of their conservatism, nothing else. I don't see a lot. For example, the best solution is, for example, they embed fiber sensors. It happens in aerospace. In fact, because fiber sensors are expensive, and only aerospace industry can afford such costs. So we only see those happening in aerospace. But at the same time, and you know fully well, you're an aerospace engineer, if they want to change a rivet, you know how long it takes. So imagine that you're going to embed sensors and in the full aircraft body and fuselage and all of that. So that's what makes it hard to penetrate. You're welcome, thanks.